Hi, everyone. This is my video for the isobestic equilibrium problem that we are solving in analytical chemistry on Thursday, the 14th. It's my first video I've made in a while, so forgive me if it's choppy. This is the statement of the problem. We had some equilibrium involving an isobestic point, and our general strategy was to recognize that the absorbance that you measure was a combination of a contribution from the ligand and the protein ligand complex. Right? The catch here is that the protein ligand complex concentration depends on an equilibrium constant. You can go back and look at your notes, but you get this long, ugly expression for how all of these factors relate to one another. Here's the first step to solve this problem. We recognize that the concentration of the protein ligand complex depended on the equilibrium constant, and that KEQ depended on the concentrations of protein and ligand. So the first step was to calculate X0 and P0 at the various conditions. The concentration is given by the initial concentration times a dilution factor. I've written the equations out here, and I've tried to show you what the specific formulas look like in the case of the ligand and in the case of the protein. Plug all those values in, carry the formulas out, and these are the numbers that you should get at the end of the day. This is basically where we left off in class. The next step is to calculate the protein ligand complex concentration using that big ugly formula. I've rewritten it here. Again, this concentration depends on the equilibrium constant, which we don't know. So we have to figure out an order of magnitude estimate for K. And here's how you might do that. When you have equilibrium problems, I can define an equilibrium constant with this definition. If you want to estimate what these values might be, right, we're going to make an ICE chart, initial change equilibrium. I hope this is familiar to you from Gen Chem. I'm not going to go into it here, and if you need some details, come talk to me. But here's how it might look. I have initial change in equilibrium for XP and the XP complex. I'm going to pick some initial set of conditions. I need to pick a condition in which both X and P are present so that you make at least some XP. Right? I happen to have chosen the second condition listed in the paper. I'm then just going to make a guess, and I randomly picked that 50% of P is converted to XP. So if I start with 3.1 micromolar P and 50% of that is converted, I'm going to get an equal amount of XP, and I'm also going to lose that amount of X. You then add up the initial and change, and you get the amount that's present at equilibrium, 6.8, 1.6, and 1.5. And now I have at least some guess for what these concentrations might be that feed into the equilibrium equation. So all you have to do is insert the numbers. Okay, I input them here. You do your math, and at the end of the day, I get an order of magnitude estimate that says K should be on the order of 1.4 times 10 to the minus fifth. So what we're going to do into Excel is add a new cell, I'll call it K, and I'm going to enter that number. I'm then going to go in and write that big, ugly formula for how you calculate the concentration of XP. I've written it out here. You can check it against mine. Make sure you have parentheses right. Make sure that you have dollar signs if you need to hold a value constant. And if you do all of this right, at the end of the day, here are the values that you end up with. Right? So I now have the concentration of PX. What I need to get next is the concentration of X. And so in order to do that, what I'm going to use is a simple mass balance statement. So the concentration of X is simply equal to the initial amount minus the concentration of XP. I have both of those values. Here's the initial, here's the amount of XP. So I can quickly calculate what the concentration of X is. The next step, I need to calculate the absorbance. Again, I'm using this formula. I have the concentration of PX. I have the concentration of X. What I need is the extinction coefficient of X and PX. How do I get that? Well, you can often calculate one from the statement of the other, and we often have to guess one of them. So if you went back and looked at the statement of the problem, the first condition right here has no protein added. It's pure ligand. And because it's pure ligand, I can simply use a Beer's law statement to calculate the extinction coefficient of the ligand. It's a plug and chug. So I plug in numbers, an absorbance of 0.0264. Here's the concentration in molar units, and you get that the extinction coefficient is 3143. I need to get the extinction coefficient of the complex. Okay, I can't get that from the problem, and so I'm simply going to guess it. And order of magnitude, I'll guess it's about the same as the extinction coefficient of the ligand. I happen to guess 3,000 inverse molar, right? I'm going to add two new cells to my spreadsheet. So here's the extinction coefficient of the ligand. Here's the extinction coefficient of the complex. I can plug both of those numbers in now and calculate what the absorbance, my calculated absorbance would be. Concentration of XP times the extinction coefficient of XP, concentration of X times the extinction coefficient of X. And if I do all of this at the end of the day, here are the numbers you get. I'm happy because they're at least reasonably close, you know, within an order of magnitude or so of the measured values. And so at this point, I can go ahead and do the least squares analysis. First thing you're going to do is calculate the residual, right? A calculated minus A observed. Plug those numbers in, and this is what you get. You're then going to square it. Plug those numbers in, and this is what you get. Last step is to sum the squares. And if you sum all of those up, here's what you get. We are ready to run solver. Solver will adjust these numbers until that sum of the squares is minimized. Again, you get solver within the data tab. It's over here on the far right of my screen. It got cut off. What we're going to do is set our objective cell, the sum of the square residuals, to a minimum by changing the input cells, the numbers that I guessed. In this case, it is the extinction coefficient of the complex and the equilibrium constant. Note, I don't have to change the extinction coefficient of the ligand of X because that was a directly calculated quantity. Put all of those numbers in, click solve, and at the end of the day, here's what you get. Excel does its thing, and I get an optimized value for the equilibrium constant and the extinction coefficient of the complex. So to close the loop, this was the problem we were trying to solve. This was the specific directive, the thing we were calculating. We're going to determine extinction coefficient of PX. Again, we get that from Excel. It's 16,200 inverse molar inverse centimeter, and an equilibrium constant 2 times 10 to the 5th. Right? Hope that helps. If you have any questions, shoot me a note, and I will see you in class on Tuesday.